bra. Ja, men då verkar det som somehow är det tillbaka till 5 minuter. Nu kommer jag dit nu. Okay, let's see if we can start this lecture in an orderly fashion. Welcome. Today we're going to talk about relational models and algebra. I've already talked about these topics a bit before, but I sort of never mentioned the words. So parts of this is a recap, and some of these topics are quite new for today. You already know by now that movies entity set, where we had that title and the year, and they were composing the key, and that key was something that uniquely identified something in that movies set. And you also know that some of these keys are better than others, and that it is quite hard sometimes to find a good key. And the keys can be just one attribute, or there might be a combination of them. And you also know that what you have here are those ovals are the attributes, and the square or the rectangle is the entity. And the next picture here, the next slide, I think I have used that notation before, but when you are turning this into a relation, or more of a something that could in the end be an actual table, I used that notation where it looks like a function where you put a lot of things into it, like a function f of x and y, z and all that. But this is actually, this is the relation in itself. So the relation is movies, and what you have here as parameters, if you would like to see it as a function, which is sort of not, are the attributes. Those are the attributes. And the underlined attributes, that's the key. So as we had before, the key is the combination of title and year. What you have here is the relational schema. It's fairly common to use that. I use it quite often to describe things because it's easier to do it on a piece of paper. Doing those rectangles and ovals takes a lot of time, it takes a lot of space to do it. So writing down by hand, that is easier. But what you do is sort of, it's your thing. Test several things out here and come to what should be your way of doing things. So, but just to be consistent instead. And the tuples. The tuples are the instances, and I think I've used that word before. An instant of an entity or an entity set, that's the tuples, or if you prefer it, the rows in the table. And you should also note one thing here. If it's a set, then the order among the tuples and the attributes has no meaning. And sometimes you make a sort of a mistake here, and you think that the instance or the tuple that starts with Star Wars always comes before Mighty Ducks. But don't make that assumption. It can come in any order. And that goes for the attributes as well here. They can come in any order. Usually when you use a actual database, let's say MySQL or one of Microsoft's, they sort of look like they always come in the correct order when you view them. But making that as a fact is false. It's a bad thing. You always use the SQL language for ordering them. That's the only thing you can do, right? So we have the schema, We also have each component of an attribute, and we will come to that later on when we are talking about normalization, is that they are atomic, can contain only one thing, which is a good thing. And they are also associated with a domain. And then a domain, as it says here, is a length as an integer. It's your sort of value domain. Where do you take your values from? And it also has a type. And the number of attributes in such a schema is the arity, and the number of tuples is the cardinality. Not that you talk that much about arity, but it is good to know, right? So if we take that schema once more, that relation, and have a look at it, and this time we have added the type. Each attribute here has been prepended with has been associated with a type. And that is something that you might do in the beginning when if you actually know what type it should be, or what domain you are talking about. If you don't know, then skip it and add those things later on when you know what it is. Because sometimes you just know that, okay, I have a title. That's fine. Add the types later, or the domains later. So having a look at that film type, we see that it's set to the domain of whether it's in color or in black and white. Well, then you have to sort of define what that color BW is. It might be easier to just tell the people whether it is in color or not, which then turns that type into a Boolean value instead. So sometimes those domains changes, and as well as the types and all that. That is something that you will find out along the process of your project. Just as long as you know that, okay, there seems to be an importance here to know whether the film is in black and white or color, right? And also when you turn that schema into an actual table, you will sort of find yourself having different domains and different value types here at hand. For instance, different versions of floats. So that is also a decision you have to make later on. Some of you might have heard of a float and a double. There are a certain difference to it. The float is a lot smaller than the double. And if you know your value domain, you also know which one you should use, because there's a difference in size. It occupies, the double usually occupies the double amount of memory compared to a float, for instance. So if that is a problem, you have to take it into account. I sort of hope that you find it more comfortable writing your schemas that way than using those rectangles. But if you don't, go on with that. So turning that diagram into those relational schemas, you have the diagram to the left and the schema to the right. You see that it takes up a lot smaller space to do it, and I find it easier to edit it as well. But that's just my preference. Find your own. So let's have a look at the studio. The studio just is composed of just the name and the address, and the name is the key. The key was that attribute or a combination of attributes that just uniquely identified something. And then you have the relation owns. So sometimes you have to make a combination of these movies and studios entities, and the relation was that square, that diamond. So that specifies something, that tells you something. It sort of connects the movies and the studios. So that sometimes turns into also a schema. And well, the question comes here then, how do you uniquely identify that relation schema? Well, you pull the keys from both the entities and move them into that relational schema, the relation. And that's what happened here. They pulled from movies the title and the year, and also name from studios. So if that owns relation would have its own attribute, then that would be also an attribute of the owns schema. And that way you can make any combination now of the movie and the studio. And this is just one way of doing it. There are some other ways as well, where you move keys from one entity over to the other one, and that's typically many to ones or ones to many. Yeah.
So, like in here, if we put in the movies like studio names,
yeah. Then you have a specific meaning to if you move the name, the attribute name of studios into movies. Then you would have just a combination of title, year, and name. And the other way if you pull it over to the other side. So, but sometimes you just go with one of the versions which suits your needs. So yeah. And the hard part is not what we're doing actually right now, moving it over to a schema. The hard part is your diagram to the left, coming to the conclusion that this is the one to use. The next phase is just start to normalizing and figuring out the types and all that stuff, and the domains and the values, so, right? Yeah. So one way of that, and that was actually what you were talking about, moving things over to the, instead of using a relational table for it or a relational schema, we came to the conclusion, which you already did, that okay, let's move the name of the studio over to movies, and we'll accomplish most likely the same thing. If we would make that studio name a part of the key of movies, otherwise it will not work. And that's perhaps something that we should do, right? So if we have had a good day of working and our model is solid, well, if we have that model, we should do something with it. We should probably extract data, or we should ask our model for information. Did a specific star actually perform in a specific movie? Or how many stars does the movie Mighty Ducks have? And so on. And that's a part of creating a database, finding out those questions. And that is the relational algebra thing. So we're going to define a few operators that operators on those schemas. And what you see here is the base for the query languages used by the databases, MySQL or one of the Microsofts. And there are a few ones. We have the union, the difference, the Cartesian product, and selection and projection. So we need to remember that if we have that sigma, we mean selection, and if you have pi, we mean projection. So it sounds quite strange, but if you have a look at it, it has a certain meaning. So when I'm saying projection, I mean, okay, which attributes am I actually interested in? And the selection are, okay, what row? There must be a condition for me selecting the tuples, and that's the selection. And if you want to combine several entities or schemas or tables, well, then you use the Cartesian product for it, and so on. So without these operators, we wouldn't be able to actually do anything, do something with our database at all. Our tables would be meaningless. We would put data into it, but we couldn't do anything with it. And there are more functions than just asking for things. There are things like updating and deleting and adding things in terms of those tuples. So this is just for querying. And those, as it says here, it's sometimes quite complex things we're going to create, because we're going to combine those operators. You will find out quite quickly when you're creating your first database, when you have a lot of tables and a lot of attributes or columns, and you start to figure out how do I actually get that information, and it turns into a monster query. It goes quite fast. So that's the selection operator. So we're going to figure out how do I get a certain amount of tuples, or those rows, or those instances. So we have the operator, and we have a condition, and that condition C actually makes us select things or remove things. And we have that relation, which turns into later on a table or a multitude of tables. So examples we have here from that movies relation. Show me or get me all those movies that has a length which is less than 100 minutes. So that sigma is the selection. The condition is what you have there as a sub-index, and it operates on the movies relation. So that returns you all the tuples for that schema, and you get back all the attributes. It returns all the attributes, but only the tuples that satisfy that condition, length less than 100. Okay. So the projection then. Well, that's an operator that we use when we are interested in just a few of the attributes. The selection returns all of them. The projection, the pi, returns those attributes that we tell it to return. So it's the same thing. We have the operator pi that works on the relation R, and then we have a comma-separated list of attributes. Those are the attributes we are interested in. So selection returns all the instances. Projection returns all the columns. And the intersection is what you get. So from the movies, we are interested in the attributes title and year. So pi, subindex title, comma year, and the relation. And that returns all the combination of title and year. We're just selecting those two attributes, and it returns all the instances of that. And that's what you have here. The new schema, as it says, is movies and title and year, but it returns all the instances for it, right? So, told you before, it works like a function, sort of. So, what if we combine these two? If we first try to sort out and remove all those films that has a year larger than 1990. Sorry, it's the other way around. We are interested in those films that are produced after 1990. So that operator returns all the tuples having year larger than 1990. And that returns a new schema with that condition met. We send that to the projection operator, where we tell it to, okay, we're only interested in the title. So what we have here is that we are returned tuples for movies produced after 1990, and it's the title we are given back. Sorry for there's a type confusion here. If you have a look between the topmost tables to the left, there seems to be a kind of an A. That's not the case. It's the selection. Sorry. So what you do here is that you are telling using your operator to return those movies produced after 1990. So Star Wars is removed, doesn't meet that condition, but Mighty Ducks and Wayne's World do. And then we send that schema over to the other operator, which was the projection, and we are returned title. So if you have a look at the right-hand side of the slide, you see that that's the shorthand of it. It's the same thing. And this is something you do through the query language that your SQL database has. But this is what happens. Okay. I think you get the hang of this. You just look at the operator and the condition and view it as a function. But that's another thing here. Or the order. If I do the selection first or the projection first, does that actually matter? Yes, it does, as it says here, because if you have a look at the lower projection and selection, well, what you do here is that you are interested in the titles of that movie's relation. That's something that is also returned. Then you start to ask for whether the year is larger than 1990 or not, but that's not okay because you told you the relation that, okay, I'm only interested in the title, so the year doesn't exist at that point. So the top one was that that's the example we had before, and the lower one here doesn't work. So order matters. Right. There is also a possibility to use those unions and differences and intersections if you want to. They are fairly common. That is sometimes easier for both you and me and others to understand, to actually do that in a combination instead of sort of sending it further down through the next operator, using and or in between. So sometimes you just make the combination right away, as you see here. If you have a look at the lower part of that slide, you see that we're interested in the title and the year, where the movies have a length larger or equal to 100 and the studio name is Fox. That's just a combination of things. That's a union of those, which for our part turns into and. So that might be the way you see it. That's a logical and you have just right to 100. That's and. I hope you have seen that notation before. The other way around is a V. That's or. So let's get the title of and year from that movie's film, where the length is larger or equal to 100 and the student name is Fox. And you get a new schema from that. So I think that's the way I am thinking. I'm thinking in terms of and all those stuffs. And you can use any sort of beans here if you want to. And that's the next question, because now we have been talking about just the movies relation. What if I have somehow a query or a question that involves several relations or schemas? Is that possible? Well, yes, it is. But what we do here is that we use that selection and projection again in combination with that Cartesian product. So we try to somehow make all the combination that can ever exist between two entities. And then we use projection and selection on that. And it's just not possible to use two. You can use any number of schemas here. But just a fair bit of warning, the more schemas you are using that are populated with a lot of tuples or rows makes one big Cartesian product of that. And then it should start to use selection and projection on that. So sometimes there are other ways of doing this, which is called a subquery, which is a bit faster. We won't be talking about that right now. So that Cartesian product is something that we are very interested in. And as I said, it makes the combination for all the tuples between those two relations R1 and R2. So if you have two large relations, there will be a massive number of combinations. So let's assume we have those two. Let's call them tables. We have the table to the left, which contains the columns A and B, and to the right we have the columns A and C. And if we put the Cartesian product to work here, it will make all the combinations that it actually can find between those two relations. And that is what happens to the right. So that Cartesian product is exploding if you're not doing it right. So you just assume you have 4 tables, and each table contains 20,000 instances. It grows quite quick. So I hope you can see that. You start off with a combination of the leftmost table, R1, taking A1 and 3, combining 1 and 3 with all the instances you have in the rightmost table containing 5 and 7 and 6 and 8. So 1 and 3, 5 and 7, 1 and 3, 6 and 8. Then you're done with the first combination, and then you move over to the other one.
So that 8 is wrong then, right?
So that 8 is wrong. It should say 6 and 8. The last row should be 2, 4, 6, 8. And it sort of doesn't matter what kind of entity you are using here. It will start to combine it. So they might not have a relation at all. They don't. To you, it might just be meaningless. But if you just use the Cartesian product, it will start to combine. So if you have a slow server, this might be a problem. If you let's assume that you have a slow server, a lot of data, and you start to use that Cartesian product. And also you have, let's assume that you have your web server, or that might be a server or your desktop application, but it has to respond quickly. It has to respond quickly. So that Cartesian product makes it go really slow. So your server or desktop app doesn't respond due to a bad Cartesian product and that slow database server. It's not that uncommon. On the other hand, if you are dealing with the internet, you have your lag there anyway. And usually you are naming it the way you have it here, the relation and the attribute. If you see here, the leftmost table is called the R1 and the rightmost one is called R2. So you see that the columns are named R1.A, R1.B, R2.1, R2.C. So that's our way of pointing out a specific attribute. To what relation does it actually to what entity does it belong, right? That's the better way of saying it, I think. But you should note that the second part here says that we use the short name unless there is a conflict. So if there is no naming conflict between attributes, well, skip that relation name if you want to. That's something you do in the SQL Server as well. So using those two, movies and stars in, if we use that Cartesian product, then that's the result you get. That's the Cartesian product, and it just combines everything and also uses all of its attributes. So it doesn't do any projection or selections at all, just combinations. Which might sound really strange here. because if you have a look at the third row, it tells you that Star Wars has a combination with Mike Myers, which isn't true, but that's the effect of Cartesian producting things here. So let's see if that actually works. So find all the actors and actresses that appeared in movies released before 1980. And we have our Cartesian product working here. So we're specifying that we're interested in the star name, which exists in the stars in relation. That's the projection. But we should also, from the movies relation, make a condition to see whether we are earlier than 1980 or not. And then we are using that Cartesian product between movies and stars in. So I've already hinted that, okay, this is not going to really work. Well, all of the movies are prior to 1980. That's okay. But we got that Star Wars and Mike Myers has something to do with each other, which is not true. So our query isn't correctly done. We're doing something wrong here. If you look at the titles, well, it seems that the Star Wars title from movies and the title from Stars In, they are not the same. They are not matching. They should. So if we add an additional part of that condition telling that selection that, okay, those two titles must be the same. The title from the movies and the title from the Stars In, they must match. Because if they don't, then something is wrong. So have a look at that selection. Well, we have that the year should be before 1980, and the title and the year between those two movies and Stars In must be the same. Otherwise, we are not correct here. So that's an effect of the Cartesian product. You have to follow up that with a matching condition. Right. A short break. 15, 10. All right, 10 it is. Exakt. Okay, we're back. So that was the last solution to it, and we think that we are quite comfortable with having that selection and that projection. So if we would run that in a SQL server, it wouldn't be that, but it would be only the titles. And you would just display the star name. If we have a look at that table, it's all the attributes, but it should just take the name of the star. Another interesting question here is that let's assume that Mike Myers is part of 2 different movies, and that would also have been a part of our projection and selection here. If you would run that query on a SQL server, you would have gotten Mike Myers twice, because they are just tuples and they are projecting, and then the selection itself. But that's not the case here. And then there's another thing here called renaming. I don't know if you really want to do this at this point. It's sometimes a part when you are actually doing some stored procedures in a SQL server. But you can, if you want to, you can rename an attribute into something entirely different if you want to make it more readable. Perhaps at this point it's easier to keep the relation name and the attribute name as they are. But just for your information, it's possible to rename things here. Okay. It came to my mind here that there aren't that many slides left, so perhaps we shouldn't have had that break for 10 minutes. Sorry about that. So this is the last thing I will be talking about, the join operators. There's a few more slides, but that's just not so many of them. So there are a few join operators here, and there are a few things you might find here if you are running a SQL server, something that is called inner joins and outer joins, and some other stuff there, which are there for you to use, so you speed things up. The natural join is something that is used when you have equality of all your shared attributes between 2 of those relations. So you have to look at the attribute names here of the relation R1 and R2. If they are shared, then they are okay. So if you have a look at R1 and look at the second row that has the attribute A and the value 2, and then you have a look at the relation R2 and its attribute A on the first row, that is also 2. Same name, same value, then they are a part of a natural selection. So that's the natural selection. You just have a look at same name, same value. So it's 2, 4, and 3. I have to admit that when I'm using these join operators, I am using what we did before. I am using the projection there and selection, and I just make sure that that equality there is better. That's the one where you have M title and S title, that they should match. So I don't think, well, I have to admit, I don't think that much in terms of natural joins here. It's just a part of database theory. There's also something that is okay, sorry, okay, so it's the same thing. That's the way I'm thinking.
What is that symbol called?
I have no idea what that symbol is called. It looks like an hourglass to me.
That's been stopped.
That has been stopped. A tilted hourglass. I don't recognize it as a part of the Greek alphabet. Is there anyone in here that does that? So that's another example. Having those matched using that natural join would give you that answer. So you just have to look at the titles and the years that they are matching, because those two were the ones that were the common. And when they have the same value, then they are part of that selection. At this point, I don't actually know when I should ever use this, but it should be known in your vocabulary what a natural join is. And then there's also a theta join, which is more a congruence between sets also. And that's the same thing, but it sort of involves a condition. And so we have that not natural join and a condition, which is the same that we had our selection before, where we had our condition and our cross product. And as we can see, that condition theta can be just about any condition we feel like, just as long as they are part of the involved relations.
So just a moment. So can we consider the first one, the natural one, as same thing, title equals?
Yeah. So the left part there, that is the theta join, is congruent, which so they sort of end up with the same set. It's the same thing as we had before when we had that dot cross product between R1 and R2 and put a condition on it, so we had a selection. They are the same thing here. And as I told, you will find me to the right-hand side of that congruent symbol, not to the left. So they are sort of a shorthand. So this equijoin is a sort of a shorthand for that theta join when there is an equality testing going on between two conditions. So for example, what we have here is we have the equijoin between the movie's title and the stars in title. And that would be our equivalent of having that selection that we had earlier when we checked that the movie's title was actually the same as the stars in title. And once again, what you have here at the left-hand hand to the left hand of the congruence symbol is the same thing and results in the same set as what you have to the right-hand side. Sorry. So this is just a shorter way of saying the same thing that we had earlier. And there's a difference to the symbols here. If you look at that tilted hourglass and have a look at the title for the slide, you see that there's a difference. the first one, there's an open end to the right, and the right symbol has an open end to the left. So it depends on whether you are doing it the left side or the right side here. So it sort of skips one of the relations here. It's just interested in one of them, but there's a condition to it. And if you have a look at that congruence symbol again, then you might say that these two relations R1 and R2 is the congruent to what you had before when you had that projection, where you are selecting just a few of them, but you are selecting the ones from one of the relations. So if you are using something is wrong here with my with the fonts here. Let's see if I can figure that one out. Hang on. So the open-ended symbol is the open end is to the right here. I'll fix that and send out an updated PDF for you. So it's that natural join, but we are just interested in the employee, the columns or the attributes of the employee relation.
So it's kind of like filtering the employees depending on the department. Can be
Yeah. If you would do using selection and projection here, you would make that selection, and you would have to check that the department.dep name is the same as employee.dep name. And then you are using projection for the employee attributes name, emp ID, and dep name. Right? And that goes the other way around as well. And then there's that anti-join, which returns the opposite of the semi-join. And you can also see that the symbol is a bit different here. There's a triangle tilted to the right or the left. And that's the combination of the semi-join. If I have a look at that expression here, if you have that combination of anti-joins, R1 anti-join with R2, it's the same thing or congruent having R1 and taking the difference between R1 and R2 when you have the semi-join. Yep. So, sorry guys. So here it comes again. That semi-join. The difference to it was that there are a check for whether you want to have just one of the relations as an answer or the other one. And you have hopefully noted, if you have a look at the symbols in the header, that there are that symbol, but there's an open end to each of those two. So the first one has an open end to the right and the other one to the left. But just once more again, have a look at the expression at the end where you have that congruence symbol. If you are taking a semi-join between R1 and R2, where the open end is to the right, that's the same thing as that natural join, but you are only interested in the leftmost of them. So just remember that you have the natural join, but you are using projection here. And so you're sort of selecting the ones from R1. And that was the example. And I did write that on the whiteboard. So when you moved over to that anti-join, we concluded that it was the opposite of a semi-join. So if you have R1 anti-joined with R2, that would return the tuples from R2, for which there is no tuple in R2. That's the other way around. And if you have a look at that expression at the end, we have the congruence symbol, and what's to the right of it, we have that difference symbol, that's the backslash. So you are semi-joining R1 and R2 and check for the difference with R1. So anti-joining employee and department returns Harry and George. Because if you have a look at it, if you would join these two and make a selection, you would connect department of both those tables. So, and you're checking for sales and productions. And it turns out that Harry and George is the only one that is not a part of the department relation. And sorry for those symbols, that isn't really okay here. I have no idea why they are like they are. I will get back to you with an updated PDF having those symbols sorted out and updated. Okay. That was the last slide for today. And let's meet again tomorrow, where we'll talk about these things a bit more. Right.
Just one question. If you go back to slide 43, maybe that was the question you asked before, but so this is wrong in that sense that the attribute should have the same name,
yep.
Employee and department, right?
Yeah.
So in this case, it wouldn't work because this is called manager and it's called.
Yeah. So if you would, the question here is, we are back at the slide 43, and why the last one is the anti of this one, is that here you are matching the department's name because those are the same thing here. So that's what is checked.
Okay, yeah.
And then you check whether they have the same values here, and they have the same values for sales and production, but not finance.
Yeah.
So the anti-join of this is finance instead. But when you start off with your queries and using an actual SQL server, you will think more in terms of those query languages and not in natural joins, semi-joins and all those. But right now you know that there is something called joins, and there are a few ones here, right? Okay. Thank you.
The next picture will be here.